All right, this is for our forces bit. So we've already taken our notes on how to actually draw forces, and now we're going to talk about Newton's laws that go along with that. So the first thing we have here is Newton's first law of motion, and most of us are familiar with Newton's laws. It's something that you have studied in the past in elementary school, so it shouldn't be anything that's really new to you. The first law is the law of inertia. So what this states is that in the absence of some sort of outside force, so that push or pull, an object that's in motion is going to stay in motion, and one that is at rest is going to stay at rest unless some sort of outside force acts upon it. So if something's rolling, it's going to keep rolling forever until something makes it stop. Maybe it's friction, maybe it's something that's actually like a barrier. If something's not in motion, it's going to stay still until something kicks it, pushes it, that kind of thing. So an object's going to keep doing what it's supposed to do or what it's doing until a force is going to change that motion, okay? And this is like the things I was just talking about, a bullet striking a wall, a ball being thrown and caught, okay? So we talked about force diagrams in the last little bit that we did. This kind of goes over that. You have an object that's originally at rest, okay? You put a force on it and it's going to move, okay? If it's equal and opposite, it doesn't move. If it's in motion, okay, and you add a force to it, okay, it can cause it to slow down. If you're pushing against it, if you're going with it, it's going to speed it up. Think about like if you're rolling a wagon down the hill and you push it, it's going to go faster, but if you're standing there and trying to hold against it, it's going to slow down. Whereas if you're pushing and pulling in opposite directions, then it's going to stay at a constant speed. All right, so the first law says that an object is going to resist a change in its motion, okay? The more mass it has, so we typically think, and sometimes we inaccurately use the word mass and weight together, but mass, how much matter is in that object, okay? If they have more mass, they're going to need bigger forces to change their motion. And so that's kind of what's going on here. If we think about this basketball player and this ballerina, who would be harder to move, we would definitely think that it would be that basketball player because he has more mass, okay? Here it says momentum, okay? Momentum is related to how much force is needed to change an object's motion, okay? It's going to depend on direction, and here we have our equation for momentum, mass times velocity. So P is going to equal to mv. So P stands for momentum, M is for mass, and V is for velocity. If we were going to draw a triangle, we would draw a triangle. We would put the P on top, M and V would go on the bottom. These units are going to be in kilogram meters per second. And so there you go, momentum is kilogram meters per second because you have kilogram over meters per second, which was your velocity. All right, so force is going to be a change in your momentum. Okay, force's equation is going to be mass times velocity. And remember, velocity was your final speed minus, well, not speed. Sorry, the change in velocity would be final speed minus initial speed. So that would be your acceleration. So F equals ma, that's our second equation there. All right, so now we move on to the second law of motion. It says change in motion of an object is directly proportional to the unbalanced outside force and inversely proportional to the mass. So what this is saying is the amount of force that you have to use, okay, is going to be dependent on how big that object is, okay? So force equals mass times acceleration. Think about if you have a tiny little kid's little Tyke's little car out in the yard, okay? It's going to take a whole lot less force to push that than to push somebody's big old Suburban in your yard, okay? So definitely more force depending on how much mass you have. All right, so here's an equation here. Force is equal to mass times acceleration. So the mass I see is 3 kilograms, and the acceleration is 4 meters per second, which we know can be 4 meters per second squared. And that's going to be 3 times 4, and that would give us 12 kilogram meters per second. But force, we can take this kilogram meters per second squared and condense it into being a newton. So here's a new unit for us, a newton. So acceleration units, remember, are meters per second squared or meters per second per second. All right, so next, we have to make sure, and I already had mentioned this before, we sometimes use these wrong, okay? But there is a difference between weight and mass, okay? Weight deals with gravity. So if you think about your weight, okay, for this little person here, their weight on Earth is 560 newtons, because that would be their force, okay, their mass times the acceleration due to gravity. On the moon, it would be 90 newtons, but the mass was always 56 kilograms. Mass never changes. The reason that the weight can be different on Earth versus the moon is because the amount of gravity on the moon is much less than the 9.8 that we have on Earth. Okay, they are not the same thing. All right, so mass is the measure of how much matter they have, whereas weight is the force of gravity acting on it. So here's our second equation, okay? The force of gravity is equal to mass times gravity. Gravity is an acceleration, so this equation does look very similar. And we have a unit here for gravity, 9.8 meters per second squared, okay? And that is what we're going to always use. That's a constant. So unless someone tells you that the gravity somewhere like on the moon or on some other planet is less, you're always going to know that G is 9.8 meters per second squared. All right, so because it's a force, you're going to use newtons as your unit, okay? And acceleration to gravity is always 9.8 on Earth, and I've already said that. Okay, so here's a question here. Jesse has a mass of 200 kilograms. What is his weight on Earth? If I want to figure out weight right here, I'm going to say mass times gravity. So his mass is 200 kilograms. Gravity is 9.8. I'd say 200 times 9.8, and I would end up with 1,960 newtons. All right, so last law. For every action, there's an equal but opposite reaction. Okay, so think about like if you've ever been in a boat and you were paddling. If you want to go forward, you paddle backwards. If you want to go backwards, you paddle forward. You push the water forward. So equal but opposite. Same thing with like a rocket being shot off into the air. If the rocket is going to go up, okay, you got a force going that way. You've got all of that thrust that comes down. So you have the equal but opposite because they're going in opposite direction. So, for example, if you've ever played softball, baseball, if not on a formal team, at least like in PE, it says a baseball bat exerts a force on the ball, therefore the ball exerts the same force back on the bat. This is why your hands sting. So when you make contact with that ball and you swing and it finally hits, the reason that you can feel that vibration in the base of the bat is from the fact that you've got the equal but opposite force, okay, what the ball had versus what the bat had. So another example here, if I push on a wall, okay, the wall's not going to move. I don't fall forward. The wall doesn't come collapsing on me because it's an equal but opposite. Okay, if there's equal but opposite, there's no movement. And we did that with our force diagrams already. Okay, all right, so that was what we had for Newton's laws, and we'll have some practice to go along with that. Don't think any of that recorded. It did not. That's fun.